This is going to be a comprehensive review of dynamic programming as a problem-solving strategy. So let's get right into it. Basically, what dynamic programming is breaking a big main problem into smaller versions of that same problem. Then we assume that we know the answer to these smaller versions, and we go from these smaller answers to the answer to the big problem. So we use them to build up to it. At a high level, that is what dynamic programming is. I'm not going to go too into detail. It'll make a lot more sense once we start solving. Okay, but here are the main steps that we want to do whenever we see a dynamic programming problem. The first one is figure out what a state is, or figure out in what sense there are smaller versions of the problem. So how can we actually parameterize the problem, and how can we specify what a smaller state is? Once we can do that, we want to find our base cases, which is the states for which we know the answer immediately. It's super quick. And after we can do that, we want to find these state transitions. So how do we go from the smaller states to the bigger state? And then how can we combine smaller solutions into the bigger solution? And finally, we want to implement. Okay, let's get right into it. So the first problem is going to be climbing stairs. There are several ways to solve this. I'm going to focus on the one that most closely matches the techniques that we're going to use to solve the harder dynamic programming problems. So you're climbing a staircase. It takes n steps to reach the top. Each time you can climb either one or two steps. In how many distinct ways can you climb to the top? Okay, so first of all, we want to figure out what our state is. So what parameter can we pass in to make the problem bigger or smaller? And there really only is one here, which is n. So let's set that up. Let's make a dynamic programming function. I'll call it dp. And we're going to pass in, I guess I'll call it I. So this is going to be the subproblem. So how many steps are we considering? So dp of I means the answer if there are I total steps. And then the one that we want at the end is going to be dp of n. Okay, so our state is going to be the number of total steps. And now let's do our base cases. So if I equals 0, we can return 1. So that's one base case where if there's no steps, then there's only one way to climb to the top, which is to not take any steps. And let's leave it at that for now. We can always come back to it later. And now let's think about our transitions. So how can we get from our current subproblem to smaller subproblems? So right now we're at dpi and our base case is I equals 0. So a smaller subproblem would be getting closer to 0. And we are given a transition here, which is that each time you can either climb one or two steps. So by kind of going backwards from I, we can climb one step from I minus 1. So one step from dp of I minus 1. And we can climb two steps from dp of I minus 2. And these are the ways that we can transition from our smaller states to our main state that we're trying to solve, which is I. Okay, but then how do we get the solution? So we know dp of I minus 1 is the number of ways to climb to I minus 1. We know that dp of I minus 2 is the number of ways to climb to I minus 2. And each time you can either climb one or two steps. So if we're at dpi, then we could have climbed one step from dp of I minus 1, or we could have climbed two steps from dp of I minus 2. So the total number of ways is just going to be number of ways if we climbed one step plus number of ways if we climbed two steps. And this kind of way of breaking the problem down and trying all of the possibilities, in this case, one or two steps, is kind of central to dynamic programming. So at the end, we're just going to end up returning dp of I minus 1 plus dp of I minus 2. And we successfully broke our main problem I into smaller states I minus 1, I minus 2. And we figured out how to combine them to get to the answer. So this is not quite going to work yet because if you notice, we are doing dp of I minus 2. So if we were to pass in 1 here, then we would get to I equals negative 1, and it would turn into a problem. So let's just explicitly handle the case of 1. And luckily for us, in the case where there's only one step, there's only one way to get there. So we can let our base case be 0 and 1. Now we don't run into any problems with this dp of I minus 2 here. Okay, cool. And finally, we can just return dp of n, which is the main problem that we're trying to solve. Now, this is a purely recursive solution, but the issue is that for every call, we're making two more recursive calls, and we end up recomputing the same value of I over and over again. And we could get around this by making some kind of dictionary. So yeah, we could make like a cache, and then we could say if I in cache, return cache I, and then otherwise we would like, set cache I to, DPI minus 1, DPI minus 2, and then we would return it. And that way we're making sure that we're not actually recomputing any value of I. But fortunately for us, because we are using Python, and Python is the best language ever, we can do this. We can just add a cache decorator and it will do exactly what we just tried to do. So it'll store all of the values we've already computed, and rather than recomputing them, it'll just return them if it's already computed. And this is from the functools library. So like normally you'd have to do like from functools import cache, but LeetCode just imports this for us. So we don't have to worry about that. In an interview setting, I definitely would either import it or just use the dictionary if an interviewer didn't understand. But hopefully this problem makes sense. This is the simplest case of dynamic programming, but oh, oops, did I forget something? dp I minus 1 plus dp I minus 2. Oh, oops. If I is in 0 and 1. My bad. Okay, this is the simplest case of dynamic programming, but this technique is going to be very effective at building up to more complex problems, as we'll see. Okay, let's move on to the next one, which is coin change. So you're given an integer array coins, so you have coins of different denominations, and you have an integer amount, which represents a total amount of money. You want the fewest number of coins to make up that amount. If that amount of money cannot be made up by any combination of the coins, return -1. And you have an infinite number of each coin. Okay, fine. So first of all, let's think about what our state could be. I think a reasonable state is just the amount we're trying to make. And then the subproblems are going to be smaller amounts. So like we're asking the question, if we know how many coins it takes to make a smaller amount, will we be able to build up to the larger amount, right? So let's do that. And oftentimes in these medium level problems, there's not going to be too much ambiguity on what the state is. If you try dynamic programming as a strategy, there's probably going to be one reasonable setup of a state. So DP, I'll add the cache decorator so I don't forget. And we're just going to say amount. And I know I'm reusing the same variable name, but I think I think that's okay. So, okay, for a given amount, let's think about our base case. I think we have a pretty easy base case here. If amount is 0, we don't need any coins to make it. So there we go. Okay, now what are our transitions? So in the previous problem, we saw that we can either climb 1 or 2 steps, and we use that as our transition. So like, what's the last step we can do? We can either climb 1 or 2 steps. In a very, very similar way, the last coin that we use could in this example, either be a 1, a 2, or a 5. So in the previous example, our transitions were given by the steps of 1 and 2. In this case, our transitions are given by the different coin values. So the last coin that we use could be either a 1, 2, or a 5. And we could have been at 10 and used a 1. We could have been at 9 and used a 2. We could have been at 6 and used a 5. So let's do that. Let's go through all of the possible coin values to get all of our possible states. So for coin in coins, we would like to see what the state is before. So assuming that this coin was the last one used, I'll say prev min is going to be equal to dp of amount minus coin. So all this is saying is that we already know the answer for amount minus coin. Like we already know the minimum number of coins to make amount minus coin. And then we can just add one to this to get an amount. Like we can just add one to this to get a way to make our current amount, right? So we could do one plus this, and I don't know, we could call this like way to make. And there we go. And now we're going through all the coins, and they're gonna have different values. Like it's going to be harder or easier to make some of these different amounts. So let's just have a solution variable. And we'll make that infinity because we're taking a min. And we'll just say solution equals minimum of solution and this value. So all we're doing here is we're saying that let's go through all the coins, assume that this is the last coin used, so the previous state is here, then that state required some number of coins to make, and then we just use one more coin. And this is a possible way to make the value. And in the previous example, we had to add the solutions to get our new solution. In this one, we're taking the minimum of all of the possible ways that we could make this amount, right? And finally, we can return the solution. Okay, there is kind of one edge case here. You always want to make sure that you're not going to go out of bounds. And here, amount minus coin could go out of bounds if amount was smaller, right? And we wouldn't want to use a coin that's bigger than our amount anyway. That wouldn't make any sense. So I'll just say if coin is less than or equal to amount, then we can actually use it. And then if none of the coin is less than or equal to amount, then we can't make it at all. And we just return infinity. So I'll say min coins equals dp of amount, this time referencing the actual problem that we're trying to solve. And I'll say return -1 if min coins is infinity. Otherwise, we can return min coins. Okay, this should make sense. There we go. And let's submit. Okay, hopefully that made sense. And we used exactly the technique that we used in the previous problem. We looked at what our states were, we looked at what the transitions were, and we tried all of them. And that is exactly what you want to do for every dynamic programming problem. So let's go to something a little different. And this is a classic. This is longest common subsequence. So given two strings, we want to return the length of their longest common subsequence. If there is no common subsequence, return 0. Okay, so a subsequence is a new string generated from the original string with some characters deleted without changing the relative order. So if you have A, B, C, D, E, you could delete the B and the D, and you could do A, C, E. So the way I like to think of it is kind of like skipping over some characters. So you're allowed to skip over some characters in the string, and that's what a subsequence is. And for a common subsequence, we basically want to find in the two texts, if we're allowed to skip over some characters, how much can we match up between them? So A, B, C, D, E, A, C, E, we can actually match up all of text 2 here by skipping B and D. For this one, they're actually the same string, so we can match every character. For this one, there's no common subsequence. So I would definitely say to pause this one, give it a try. It's a really good problem, in my opinion. But okay, let's get to work. So first of all, we can check our constraints, and looks like both the lengths are under 1,000. And in Python, we can typically handle up to 10 to the sixth operations comfortably. So if we wanted to, we could have our state be an index in both of these. And with problems like string problems, array problems, the index is almost definitely going to be included in the state. And in a problem like this where we can include both an index for the first one and the second one, let's do it. So here we go. dp of I and j, and we'll just say nm is length of text 1 and length of text 2. So we are setting n and m as variables just to make it a little easier to write. And okay, our interpretation here is that I is the index that we're in text 1, j is the index that we're in text 2. So, okay, let's think a little bit about what this means. The way I like to think about any sort of index in a dynamic programming problem is the we're starting at that index and we're trying to solve the problem starting from that index until the end. So dp00 would be the entire solution. And then the smaller states are actually going to be the ones with larger indices because we're getting closer to the end. Okay, thinking about it that way, our base case is going to be pretty simple. It's going to be that we're all the way at the end. And in fact, if we reach the end in either of these strings, we can't make any more longest common subsequence. We're done. So that's going to be our base case. So if I equals n or j equals m, just return 0. We don't have a longest common subsequence because we ran out of one of the strings. One of them is empty. Okay. That's fine. Now, moving on, like I said, we want to try everything. And like I said, for subsequences, that means that we can skip over characters. So let's make one variable called skip1, and that's going to be dp of I plus 1, j. So we are skipping over a character in text 1, which is a valid thing we can do. And we're skipping over a character in text 1, and we're keeping text 2 the same. Okay? Another thing we could try is we could skip 2. So that's going to be dp of I and j plus 1, where we're just skipping over the next character in text 2, but we're keeping where we are in text 1. So these are kind of ways to adjust. And for example, here we might like match the A's, but then we want to skip over the B. So we would be handling the skip 1 case, and we would be going to the C. Those are two possibilities. And the final possibility is actually if we skip both. And there's a situation where it's beneficial to skip both, which is that, if we have the same character, like A and A, then we want to match them and then go to the next in both. We don't want to just skip one or the other. So I'll say skip both, but this isn't even skipping both. This is take both. This is going to be dp of I plus 1, j plus 1. And in this circumstance, it's actually possible that we increase our longest common subsequence because if those characters match, then we have an additional character in our subsequence. So we'll just say um, text 1i equals text 2j plus dp of I plus 1, j plus 1. Essentially, what this is saying is that if our current characters match, then we add one to our solution and we check advancing both. So these are all of the things we could possibly try. Skip 1, skip 2, or actually just advance in both. And then if we're able to add one to our solution, we do. We've matched something. So those are all of our cases. And naturally, because we want the longest common subsequence, we just want the max of all of these. Uh, and technically, in this take both case, if the characters don't match, then we're just going to dp I plus 1, j plus 1, which is something that would be covered by these two cases eventually, but that's not a big deal. Not a big deal to cover it both, and it's a little easier to write, so I'll take it. Let's add cache, and let's return dp00, which, as we talked about with these indexing problems, I think that this is by far the easiest way to think about it. Okay, and we can submit. Perfect. And it is getting a little harder, but This is a very standard pattern, especially with string problems when you have two of them. You're going to have indices of both, and then you're going to have various things to try. So I even have another more complicated example of something similar coming up. Let's go to the next one. This is actually a hard problem, and we will see why when we start trying to solve it. So you're given an integer array prices, where prices I is the price of a given stock, so list of stock prices, and an integer k, and you want the maximum profit. So you can only do at most k transactions, so it can be less, but you may buy at most k times and sell at most k times. So given our list of prices, we can buy and sell at various times. May not engage in multiple transactions, so we can't buy and then buy again. So we can buy and then we have to sell before we can buy again and then sell again and so on. And we can only do that at most k times. We want the max profit. Okay, not too complicated. Again, I would recommend giving the problem a try. Not complicated to state, at least. Okay, so speaking of state, let's think about our state. So okay, one reasonable thing that we definitely need to have in our state is going to be the index. Like we're going to need the index of prices that we're on that we are continuing from, right? Okay, so we have the index that we're on. Then what else constitutes a state? Because we could be on the same index, but we could get different answers if we have different number of transactions remaining, right? So if we're at index I, but we have k transactions left, that might yield a different result than if we had zero transactions left. So it actually ends up being necessary to encode our transactions left in our state because for different values of transactions left, we can get different solutions. And this is okay because the price's length is 1,000 and then k is 100. So multiplying those together, we get 10 to the 5. So we can actually have both of these things in our state without worrying too much about time or space complexity. Okay. And then in addition to that, we actually need something else because even if we have the same index and the same transactions left, something could be different. And it deals with this multiple transactions case where we could hold a stock right now, which means we can only sell it, or we could not hold a stock right now, which means we can only buy it. So I'll just call it held. And this means whether we are currently holding a stock or not, because that changes what options we have available to us. And that's going to be our state. And that's something that you need to come up with a little bit of trial and error, but it ends up being the only reasonable state you could really have. As for base cases, uh, let's let n equals len prices. And yeah, if I equals n, that means we exhausted our whole list. There's nothing more to buy and sell, and we can't make any profit. So we're going to return 0. And all right, moving on from that, we could handle the do nothing case, right? Like that's something we could do. We could just completely skip over the current price. We can ignore it. So I'll say our solution is equal to the do nothing case, dpi plus 1. So we advance the index, but we keep the transactions the same and we keep held the same. So nothing has changed about our state. We've just skipped ahead a bit. Now, if we are actually holding the stock, then we could sell it. And that doesn't consume a transaction because I think they define transactions here as a buy and a sell. So buy and a sell is a transaction. So let's say that the buy is when it becomes a transaction. So selling doesn't consume a transaction. So if we're holding an item, it's always available to us to sell. So since we're trying to maximize, we maximize our solution with the possibility of selling. So if we sell at the current index, we gain prices I dollars, and then we move on to the state I plus 1, and we didn't use any transactions. And now we are not holding an item, so we're at false. Okay. Then otherwise, if we want to buy, we need to have transactions left. So transactions left needs to be greater than 0. which in Python is the same as just saying transactions left. This just means transactions left is not equal to 0. Then we can try buying. So we try buying, then we lose prices I dollars because we're in debt now. And then the next state, we advance by one index. We used up a transaction and we now hold the stock. Finally, we can just return our solution. So the difficult part about this problem ends up being figuring out this state. But once you have the state, figuring out the transitions is quite intuitive. And there's only three things you can do. You can do nothing, you can buy, you can sell. So here we go. Let's return dp of 0. And then initially we have k transactions left, and we do not hold anything. Okay, let's give it a try. There we go. And let's submit. Interesting. Wrong answer. Okay. Let me go through this code and see if there's anything concerning here. So we don't use anything. Oh, when we buy, we actually need to consume a transaction here. So let me use this test case, run on it. Okay, and now let's submit. It's a little weird that the sample cases didn't catch that, but here we go, and accepted. Okay, again, just as I was reiterating, the same exact technique that we've been using even for the very easy problems does work for much harder problems. Now to move on to by far the hardest problem that I'm going to address, it's going to be wildcard matching. So another string one, we're given an input string S and a pattern P. We want to implement wildcard pattern matching with support for a question mark and star. Question mark is allowed to match any single character, and the star is like a wildcard that can match any sequence of characters, even the empty sequence. So we can completely skip over it if we want to. And this matching should cover the entire input string. And we just want to return true or false, whether or not the string matches the pattern. So A and A, there's no wildcards here. They're just different strings. So it's going to be false. In this case, the star can match anything. So the star can successfully match the AA. In this case, even though the C matches this wildcard, the B does not match the A. So we don't match. And yeah, we could have something like a wild card, something after a wild card. So like this could be wild card A and it would still match AA, but it wouldn't match something that didn't end in A. So, okay, hopefully the problem makes sense. I do encourage you to try it on your own. It is significantly harder than the ones that we've been trying so far, but let's get to it. So with string problems like this, and given the constraints, we should have our state be the index in both of these. That is a reasonable state to pick and try. So we're going to have I and j, and we'll say n equals len s, sorry, n m len s len p. Okay, now let's think about our base cases here. So obviously our base cases are just going to be we reach the end of the string. But because S and P are not symmetric, there is going to be a difference in whether we reach the end of S versus we reach the end of P. P is a pattern. So let's first consider what happens if we reach the end of S. So if we reach the end of S, then I is N, right? Okay, so we have no more characters left in I. One case that we actually do match is if there's no more characters left in P. So we can return we can return J equals M. So this is one situation that could happen. We reach the end of S, but then we also reach the end of P. So this is a successful match. But we could also have a case where even though we haven't reached the end of P, we could still match, specifically because the wildcard matches any sequence of characters, including the empty sequence, if all that's left in P is a bunch of wildcards, we technically still match, right? So PJ is a wildcard. And yeah, so PJ could be a wildcard, which means we are currently matching. And to advance and check that they're all still wildcards, we could say dp of I j plus 1. So we basically we basically either need to be done with P or we need it to be a wildcard. And this dp I j plus 1 is just a way to check the next character of P and see if it's still a wildcard. Perfect. Now, if J is M and we did not reach the end of S, that's a problem. So we still have more things. Yeah, we still have more things left in our pattern, and we didn't reach the end of S. So I think we can just return false here. Think about it a little bit. Yeah, so we have reached the end of our pattern, but there's nothing left in S. So yeah, there's not even wildcards left in our pattern. We are past the end of our pattern, and there's still things left to match, so this is not a match. False. Okay, that was our base case. And in this problem, like in the previous problem, the state was the hard thing. In this problem, the base case is the hard thing. So it kind of just depends on the problem here. Okay, let's consider our transitions. Now, the case where P is a wildcard, or specifically the star, is a little weird. So let's handle that transition on its own. So if Pj is equal to a star, what are the options that we have? Like we want to try everything, right? If it's a star, it could technically match no characters. So we can just skip over it entirely. So we could do dp of I j plus 1. So we're just skipping over the star. We're saying, okay, the star has matched nothing and we're moving on, right? Additionally, we could do dp of I plus 1 j, which means that the star matched the current character. So we move on to the next character, but we still have the star. So like, for example, in this case here, the star would match the A, and we would move on to the second A and keep at the same index in P. So that's what the star allows us to do. Either we skip the current index in S, or we skip the star. Sorry, I think I got it backwards, but it's fine. We can do either of those things, and it's fine. All right. Now, if PJ is not the star, then we absolutely need the current character to match. If the current character does not match, then we we can't have a wildcard match because we don't even have the star. So I'll say cur match equals SI equals PJ, or we could also have this question mark operator here. So in both of these cases, we do have a match on the current character, and we can return that we have a current match and that the rest of the strings match. So that's I plus 1, J plus 1. So we need the current characters to match. We need the rest of the string starting at I plus 1 and the rest of the pattern starting at J plus 1 to match here. And that should cover all of our cases. Return dp of 0, 0. Let's see what we're working with. Okay, let's submit. Okay, perfect. And yeah, that was significantly harder. There was a lot more casework, but really about not giving up and just working through all of it. Because at the end of the day, you just need to try all of the cases. And that's exactly what we did here. So I hope you found this video helpful. Obviously, I covered a very wide range of difficulties, so hopefully everyone got something out of it. And dynamic programming is one of those techniques that it just takes a lot of practice. But once you get a lot of practice, most problems are very similar, and you'll have very good intuition on how to set up your state, how to set up your base case, and then how to set up your transitions, even as the problems get very hard and even as they may compose many different topics together. And I do intend to make more videos like this for more different topics.